Hello everyone, welcome back. Today's video is testing right here.
What is that?
So this is a ZVS driver. I'll start this video by saying this is an absolute pain to make. Like really, it dies all the time. In my personal opinion, through trial and error, the best MOSFETs for it, IRFP 250N. I recommend buying those from a trusted source like TME, Mauser. Don't buy them from AliExpress because they're likely fakes. I have here IRFP 250s, so they're probably fakes. Now I have here this 10 millihenry coil. The most important thing about it is that I made a case for it. So I put I sticker bombed all of it, and I have a hole right here for a DC port hot glued together. It's not important. So the circuit schematic for it is this. This is the exact circuit schematic for it. I'll start by explaining this. First, you can see I have here these resistors, the gate resistors, that are 330 ohms. So I got here these 333 ohms, and how I made them exactly. As you can see in my circuit, instead of using just one big resistor, one 333 ohms, I got three 1 kilo ohm resistors, because these have a lot of power they need to dissipate, but it's not exactly 1 watt. It's like half a watt. Now, the resistors are all connected, these starts, and they're also connected to the chokes, the inductive chokes. This is a 100 microhenry choke. It's rated for a ton of amperage, like 10 amps. This is made to stop the power supply fluctuations, and we'll talk about that later because it has to do something with resonance. For now, we'll talk about the MOSFETs. Other MOSFET gate protection, if you're gonna run it at more than 12 volts and you want it to not die, you need to have a pull down resistor. This is 10 kilo ohms and a 12 volt Zener diode for gate protection. So this is the gate drive circuitry. Three 1 kilo ohm resistors in parallel actually, and the pull down resistors and the Zener diodes. Also, these diodes right here, these need to be high voltage fast diodes. I chose the UF 4007 because it's the most common diode used. It goes from the gate of one to the drain of the other one. The sources of the MOSFET, the source is tied together and goes to ground, so all ground is here. I have pretty sloppy soldering, most of it is just wires. These are the diodes right here. These are the MOSFETs. These are the source of the MOSFETs directly to ground. I chose wires to do this for easier repair. These are the positive and negative connections. Right here are the inductive chokes. And now talking about the resonance part of the circuit. So you switch the big capacitor and a kind of small inductor that's 10 times smaller than the choke. So I have 10 microhenry and a 1 microfarad. Now, as you can see, I chose a pretty big capacitor. This capacitor will take a lot of current, a lot of voltage, and at pretty high frequency too. So you need a pretty beefy capacitor. I use these capacitors made specially for induction heaters. So they're tested at 50 kilohertz, but they're pretty small. Here I put 1 microfarad. This capacitor is 0.33 microfarads. So this is a ZVS circuit made for actually running transformers at high frequency, so it won't hurt you. But I have another ZVS that I'll show later that is much less refined and isn't even on a PCB, that I made with actual genuine TME IRFP 250 MOSFETs, and that circuit never dies. I'm telling you, just get the right MOSFETs. This circuit is super picky about its MOSFETs. After that, you need the good diodes, good capacitor, good inductor. So let's say this inductor is duct tape right now, right? But if it was not duct tape and I stretch it out a little, it could like 4x my current draw. Your current draw could be less than 1 amp with this inductor, and if you stretch it a little bit, it could be 16 amps. This circuit is a power hungry monster. Anyway, let's see the other ZVS. Screenshot this circuit diagram. We'll keep this nearby. I explained the whole MOSFET gate drive circuitry and the resonance. I'll put it right here. And now I have this. This is the monster ZVS. So first of all, we have this heatsink. On the heatsink is the cool side of a Peltier module. Now the operating of this is kinda horrible. First of all, you cool down everything with the Peltier module to about 0 degrees Celsius. So you give it like 12 volts, 5 amps for a long time. You could use a fan, but the heatsink is pretty big, so I don't need a fan. And I have the whole gate drive circuitry in midair. I have some wires because I did not do it right, like for this diode, but this is tying the MOSFET source together. This is ground. pull down resistor, pull down diode, zener diode, input resistor, 3 resistors. And here it's actually not completed yet. I took out the transformer from it, and I have these 2 coils and these big capacitors. They're about 1 microfarad. They're smaller capacitors and they have a way lower frequency. So this is a lower frequency ZVS. If you touch it, you're kind of dead if you touch the output of a transformer. It's not that low frequency, so you're not instantly dead, but you're pretty burnt because it's high power. The more capacitors you put, the higher the power. The less capacitors, the lower the power, but the higher the frequency. This circuit is a beast, so just get the original MOSFETs. On this one, actually, I have the RFP250M. That's what I received from AliExpress. That's another thing, you will receive fake components. I'll retire the ZVS because it's way too strong, honestly. And the amount of high voltage this survived arcing over from the secondary to the primary and to the ZVS itself. This survived like a few tens of kilovolts actually. Now that everyone has seen the ZVS, so this is how it looks like. 2 MOSFET, 1 capacitor, inductors, and the gate drive circuitry right here. I will put this in the case. So I have this fan with a little hex on it. I have this hole for power cables, this hole for DC port. As we can see, this is pretty nice. It's a big fan, 12 volts, and I can put this here. Wait, close the fan. I even printed a hex for it. I'll put this in here with my power cables going out first, so I can put them in the hole. They come out here. This is nice. This isn't dodgy. The other ZVS, you can call it dodgy, but this is a super nice circuit. One of the nicest circuit builds I ever made. Everything is in, power is in. Now, why did I print this whole fan enclosure? For the diodes, everything heats up in a ZVS. The inductors, the MOSFETs, it's pretty efficient because it's a soft switcher for the MOSFETs. It gives you a half sine wave on the MOSFET gate, so it is a pretty good soft switcher. And it works with 2 MOSFETs, so it's like less heating per MOSFET. But there's a problem with it. Start up and turn off. That's pretty bad. It's honestly horribly bad. Now, I have come with some fixes to the issue, like putting a big capacitor. Also, another very big issue with the ZVS is, as I said earlier, the MOSFET efficiency. Yes, it's soft switch, so that makes it very efficient, but it's also very inefficient because you kill a lot of MOSFET. This circuit can give a lot of power, but it's not stable. It's walking on a very thin line, so it's the most unstable circuit you could ever make. It can be pretty stable if you have the right MOSFETs, but even then it's still pretty unstable compared to something like a full bridge. I'm gonna turn on my power supply. Another bad thing about this is that you need your power supply to be turned on to the right voltage before you plug it in. You need a 12 volt power supply, you connect it. I took out one of the cables and now you plug it in. Yeah, the fan is on and now I plug it in and it's dead. Whoopsie. It's dead. I've replaced that broken MOSFET, so this circuit likes eating MOSFETs for breakfast. Also, I changed out the Wago connector because that's also a point of failure for this circuit. If something doesn't work, it's forever shorted out and your MOSFET just dies. Let's connect everything and let's see. Finally! It works. It works now. After like 2 MOSFET deaths, both of my MOSFETs died. This circuit is horrible. Yeah, just get a stable connection here. I don't know why they died. Maybe because they were cheap and Chinese. Maybe because the connection was bad. It could be my fault, yeah. Now, since I complained about this circuit for like 12 hours, I have to do some experiments on this circuit, so you don't have to build this annoying circuit that kills MOSFETs for breakfast. So yeah, now let's reconnect something. Reconnect it, yeah. Every time you connect it, there's a chance that it dies. So now this is horribly tuned, but it's still some wireless power. If I tune it, what happened? I'll do that later. But now, if I put some iron in it, the current consumption goes up. So from 0.3 to 0.5. And if I put some more iron, it goes to 0.7. Now I have here this thermocouple. It's a false reading. Yeah, it's a false reading because of the ZVS. I guess the ZVS induces some power in it. Pretty toasty. The ZVS definitely induces power and stuff. For a fact, it can turn on LEDs. Good, and this is hot already. Another interesting thing you can do with this circuit. So I have, I'll power it on once again, yeah. Let's see if it can turn this relay on. Resonating relay. nothing. But it will help, this capacitor will help. My coil will light up, yeah, a bit farther away. Yeah, I disconnected the capacitor. But that doesn't matter. We're not here for induction heating or for like playing with current and stuff like this. All of this is pretty nice and toasty, but let's turn on the fan. So we're not here for this stuff, right? We are not here for this. What we are here for is transformers. And I'm gonna power everything up. Nope, nope. Too bad, too bad. This circuit can die from anything. It died from me powering it on with my power supply instead of pushing it in, because the power supply doesn't turn on instantly, so there's a voltage increase. So it died from that voltage increase. The oscillation stopped and it died from that. Yeah, that's pretty bad. That you literally have to plug it in, which is why I designed the circuit for turning it on automatically. And for that, I have here this extra circuit today, testing right here. So this is a soft starter that's mixed up for high voltage. You have the negative that I drew as ground. Feel the circuit schematic real quick. This is just the soft starter, and then this is the secondary soft starter. This is basically a second soft starter that instead of starting something, stops it after 15 seconds. You power your circuit on, you get your like high voltage footage, and then you stop it. So yeah, this is the circuit I have designed. I will use this later. I didn't build it right now. Let's power this on at 14 volts. I have rubber insulated boots, don't worry about me. A bit stronger, yeah, a bit stronger. Draws about 2.5 amps, yeah. Overall, these arcs are nothing compared to what I have achieved in the past with other transformers, so I'll put that on screen right now. Anyway, see you next time. This is about it for today. Don't build this circuit, it's an insanely complicated circuit. It has 14,999 reasons to die. Stick with other stuff, invent stuff, stick with the circuit I built with the soft starter for other stuff. I'll put this once again here. That's about it for today. See you next time.